All right, let's just jump right into it. We've all been there, right? You're trying to have a conversation with a voice AI, and there's that pause, that awkward silence that just kills the whole vibe. Well, today we're going to pull back the curtain and figure out exactly why that delay happens, and more importantly, how engineers are in a race to finally get rid of it. It's such a simple question, but the answer is surprisingly complex. You ask something, you're ready for a reply, and what do you get? Silence. That little gap is what breaks the entire illusion, constantly reminding you that you're just talking to a machine. So what's actually going on in that silence? So you ask a totally normal, straightforward question. Your side of the conversation takes, maybe 2 seconds? And you're expecting a response pretty much just as fast. But instead, you get those 3 little dots. That silence is what we call latency, and it's the time the AI needs to figure everything out. Every single millisecond that ticks by makes the conversation feel less like a real chat. Let's break down what's actually happening during that pause. Okay, to figure out where the delay is coming from, we have to look under the hood at the whole process. Every single time you talk to an AI, it's actually going through a 3-stage assembly line. It has to listen to you, then think about what you said, and finally speak back. Seems simple, but each step is its own little technological miracle. This whole setup is called the voice-to-voice pipeline. First, you've got automatic speech recognition, or ASR. That's the listening. Then comes the large language model, the LLM. That's the brain. And finally, text-to-speech, or TTS. That's the voice. These 3 have to happen in order, and the total time they take, well, that's the awkward pause.
First up, we've got the ears, the ASR system. Its one and only job is to hear what you just said and turn it into plain old text that a computer can understand. In the study we're looking at, they're using OpenAI's Whisper model, which is super accurate, but it's not instant.
Next, that text gets zapped over to the brain, the LLM. This is where the real magic happens. It reads the text, understands your question, and figures out an intelligent answer. For this experiment, the researchers used GPT-4o Mini, picking it specifically because it's a great blend of smart and fast. And finally, we've got the voice, the TTS system. You see, the LLM's brilliant response is just text on a screen until something turns it back into sound that you can actually hear. This last piece of the puzzle takes that text and generates a human-sounding voice. Okay, so we've got our 3 suspects: listen, think, and speak. To make this whole thing faster, we have to play detective for a minute. We need to figure out which one of these steps is the real time thief. Where's the bottleneck in this whole conversation? So when we look at the actual numbers, one thing just screams out at you. The LLM, the thinking part, takes over 2 seconds. That seems like the obvious problem, right? But here's the twist. We feel the delay from the second we stop talking to the second the AI starts talking. This means that even though the LLM is slow, the time it takes the TTS system to make that very first sound, that's our biggest opportunity to make things feel faster. And this is the key insight. The goal isn't just to make the whole process faster, it's to make the AIs start speaking sooner. Just hearing that first word quickly can totally change how responsive the whole system feels. So the new target becomes the text-to-speech component. But as you can imagine, making it faster comes with a pretty big trade-off. And this brings us to a classic engineering problem, a real tug-of-war. You can have something fast or you can have it perfect, but getting both is tricky. For AI voices, this whole dilemma boils down to a process called Residual Vector Quantization. Now I know that is a serious mouthful, but the idea behind it is actually pretty straightforward. RVQ is basically how the AI adds layers of fine detail to the voice, making it sound rich and realistic instead of all flat and robotic. Probably the best way to wrap your head around this is to imagine an artist painting a portrait. With just a few quick strokes, you get a basic sketch. It's fast, and you can tell it's a face. But to turn it into a masterpiece, the artist adds layer after layer of paint, for shading, for texture, for all that tiny detail. Each one of those layers is like an RVQ iteration. More layers give you a stunning result, but it also takes a lot more time. So the engineers had a choice to make. The standard way uses 32 of these iterations. That's the masterpiece. The voice sounds incredible, but it's slow off the starting block. The other option, they could cut that number in half, down to 16 iterations. That's the quick sketch.
The voice would still be good, but not perfect, and it would start speaking way faster. A quick sketch versus a masterpiece, it's a great way to think about it, but engineers need cold, hard data. So they ran the tests. They measured the speed, they measured the quality for both approaches. Let's see what they found out. And wow, the results on speed are just staggering. The standard high-quality model took almost 1.4 seconds just to get its first word out. But by cutting those iterations in half, the optimized model fired back in just 641 milliseconds. That is more than twice as fast. It completely changes the whole rhythm of the conversation. But remember that trade-off? Here it is. This chart shows the audio quality, measured in something called signal-to-noise ratio. Basically, how clear is the voice? Higher is better. The standard model is fantastic, way up at over 33 decibels. The faster, optimized model, it drops all the way down to about 7. It's a huge, measurable hit to the audio quality. This is the sketch versus the painting. But let's look at one last really powerful number. It's called the real-time factor, or RTF. A factor of 1x means it takes 1 second to generate 1 second of audio. Anything less than 1 is faster than real-time. The optimized model? It clocks in at an incredible 0.48x. And what that number really means is that the AI can create a 1-second clip of you talking in just under half a second. This is huge because it guarantees that once the AI starts talking, it can keep generating the rest of the sentence so fast that you'll never hear a stutter or a pause. It can always stay ahead of the game. So let's step back for a second. We have an AI that speaks twice as fast, but doesn't sound quite as perfect. Why is this such a big deal? What does this really mean for how we're all going to be talking with AI in the future? It matters because the feel of a conversation, the rhythm, is often way more important than technical perfection. A faster response makes the AI feel more present, more natural, less like a robot. I mean, think about it. For customer support over the phone, you're already on a low-quality line. You don't need perfect audio. You just want an answer without a frustrating delay. This research really paves the way for smoother, real-time conversations with AI for everything. Which really brings us to a final question to think about. When we talk to other people, our conversations are never perfect, are they? We stumble over words, we pause, we say It's the rhythm and the flow that make it feel real. So as we build these AIs, what should we really be aiming for? The flawless, perfect voice of a machine? Or the imperfect but perfect feeling rhythm of a real conversation?